We start by getting to the last example that we had. We defined the null space of A. What is null space of A?
Ax equals 0.
So it is the x, the column vectors of x in Rn, where Ax is equal to 0. Imagining that A belongs to Rn by n, right? Rn by n. And then we give a question. Find the null space of this matrix. This matrix. And then I said that geometrically, what does it represent? So, did you try to solve it?
I think that we can use it to show linear independence of the vectors. So, using the null space.
Yeah, well, I mean, we know that the rows are linearly depending on each other, but the question is that what is the null space? I mean, we can always calculate, I mean, if it exists, we can calculate the null space. So what is the shape? I mean, if you want to write Ax is equal to 0, so A multiplied by x1, x2, x3 is equal to 0, right? Mm-hmm. Which means that x belongs to R3. So the question is that what is x and what does it represent geometrically? So 1, 2, 3, and 4. Let's, this is row 1, row 2, row 3, row 4, right? Let's have this blank is not working anymore. Blank. Let's have in the first row, new first row will be R2 minus R1. So it will be 1, 0, 1. Then I have 2, 1, 3. Then I have 3, 1. Don't write it because I will do all the operations in one go. Then I will come and I will make this new R2 is 2 new R1 minus R2, then it will be 2 minus 2 is 0, 2 minus 1 is 1, 2 minus 3 is minus 1. Then I am producing a new vector which is R1 plus R2 minus R3, but the new R1 plus R2 minus R3. If we do it, we will get to this one. And if we do R1 plus R3 minus R4, new R1 plus R3 minus R4, we will get also 0, 0, 0. You can check this.
So this is the reduced row form.
Yes, yes.
So
I mean, you can solve it in any form that you like to. This needs to be solved. How you want to solve it, it's up to you. We are not bonding you to any specific methods. But if we make this one 2R1 minus this, we will get actually this. Now, this multiplied by x1, x2, x3 is, which results into x1 is equal to minus x3, x2 is equal to minus x3. Right? One trivial solution is, for the knowledge space, one definitely trivial solution is, what is the trivial solution for this equation?
X is not a vector.
No, trivial solution. X not a vector means no solution. One absolutely always a solution is, what is the always a solution for x to make ax is equal to 0?
X 0.
X is 0. This is one trivial solution, right? Because no matter what is a, if x is 0, we get 0. But the other solution is this. If x3 is minus 1, x1 and x2 are 1, right? But we understand that we have to solve it in a parametric form. In other words, we say that if x3 is minus t, what we get, x1 and x2 are t, right? Right? So I can multiply this one by alpha and say that x, the vector x is equal to alpha multiplied by 1, 1 minus 1. This is always the solution. So what does it represent? What does this represent? Geometrically?
Mirroring around the xy plane?
No. Geometrically, what does it represent? You have to say it represents a point, it represents a line, it represents a plane, it represents a hyperplane, it represents something. It represents a cube, it represents a sphere. What does it represent? Not what property it has.
Point. It's vector.
A point.
A vector.
How many values for alpha do I have?
Okay.
Infinity many, so definitely not a point. Definitely not a point. So, but we have infinity many points. So you have to see that what is the relationship of these points. You draw it. What is that?
Line.
It's a line. Then null space is, this null space of course is a line in R3. What would happen that if we had two parameters changing? Let's say x3 was t, x2 was s, and x1 was just a combination of them. Then what does it represent in R3? If you might remember it from high school geometry, if one of them, this trio, if one of them is changing, it's a line. If two of them is changing, it is a plane. And if all the three are changing, it's a hyperplane. Now we want to talk about something new. So this is supposed to be like your work to be done.
Is this solution definite or is it
We don't care. It can be definite, indefinite. We don't care. But what we know that the solution always exists. Not always exists. There is always a trivial solution, which is 0. squash this thing. And we want to talk about something which is quite important in general, and it's called span. It's important because the next thing that we will define from span is much more essential for us in the computer science. The set of vectors v1 till vn are spanning. What is this? It's a vector space. So are spanning the vector space V if 1, v1 till vn all belongs to our vector space. 2, for any u belonging to our vector space, we have u is c1 v1. Any vector that we have is a linear combination of all these spans. And then, we show it as, so notation wise, we show a span by SP. A bit later, we add one more condition on top of this, and then we introduce something very important.
But these conditions, is it, what is the difference between just base vectors? Or?
Yes, one more condition, it makes it base.
Okay.
And I will do an example soon, you will see. Just as if you are very excited to know, is that base vector is always a subset of this span. It might happen they are equal, but a span can be bigger. So, as usual, let's do an example. And the example is this. Check if the following vectors are spanning R3. Our vectors are, let's call them U, V, and W. So in order to see if they are spanning our R3, we have to just simply check these two conditions. If I am writing fast or sound, let me know and I slow down, okay? Obviously, R vectors belongs to R3. I mean, they all have the 3 elements in the column vector, and they are all real numbers, so it belongs to R3, there is no doubt. Right? First condition done. Now for the second condition, we have to do this. Let's assume that R belongs to R3, okay? And we want to see that if R can be represented as AU plus BV plus CW, where R, A, B, and C are belonging to our field, which is R. So this means that A plus B plus 0C is equal to R1, 2A plus B plus 2C is equal to R2, A plus B minus C is equal to R3. Right? Look what I'm doing. A multiplied by this, plus B multiplied by this, plus C multiplied by this is R1, R2, R3, R vector. Right? This means that R1, R2, R3 is A multiplied by U1, U2, U3, plus B multiplied by V1, V2, V3, plus C multiplied by W1, W2, W3. Now, what happens? I write it in the matrix form. So what do I have to check? If U, V, and W are, if they are spanning R3, what should be the condition? If U, V, and W are spanning R3, the above equation should have a solution. Right? If it doesn't have a solution, it means that there exists a vector u in R3 which I cannot create it by a linear combination of my span vectors. So it must have a solution. Now the question is this, that do we have a solution? Now what is the condition in order to check if there is a solution? I mean, for me, finding the solution is not important. Important thing is that to show that there is a solution. Whatever it is, we have to show that there is a solution. And how we do it, I call this one A. One can see that determinant of A is not 0, so as a consequence, we have a solution. What will happen if we have many solutions? Is it still spanning? Yes. It is still spanning because it doesn't say that this is a unique form of representing it. As far as we can create it, then we are right. Like even if you can come with an example, like you don't care about this one, and you say that okay, any vector R1 can be created by, you come with some numbers, then it means it's okay. But you should keep the R as an symbolic vector. Let's have one definition, and then we introduce a new thing. The vectors u1, u2, un are called linearly independent if and only if. IFF means if and only if C1 U1 plus C2 U2 plus Cn Un. If this is 0, then C1 is equal to C2 is equal to Cn is equal to 0. If the linear combinations results into the 0, it has only one answer for the coefficients, which means that all the C's are 0. Otherwise, they are called linearly dependent. Comment on linearity or linear dependency, or independency of U1 is minus 2 and 1, U2 is minus 2 and minus 3, and U3 is 4 and minus 2. In other words, we have to write that C1U1 plus C2U2 plus C3U3 is equal to 0. Either we come with an example which one of these C's or some of them or all of them are non-zero, and we get this equation satisfied, which means that then they are linearly dependent, or we prove that for any like in this shape there is only one solution, and it is C1 is equal to C2 is equal to C3. So, are they linearly dependent or linearly independent?
I have this weird intuition that they have to be linearly dependent.
That's very true, because this intuition will lead us to the next thing.
Okay, because they are two-component vectors.
They are in R2.
Yeah.
We call it they are in R2.
And there are three vectors.
So it means that you have to come with a counterexample. Do you have any counterexample here? Which means that, do you have any value for C1, C2, C3 which are not 0 and it results into 0?
Minus C1 is minus 2 and C3
minus
is
2 U1 plus 0 U2 plus U3 is equal to 0. which means that C1 is minus 2, C2 is 0, and C3 is 1. And actually, this can be t, this can be minus 2t. Which obviously C1 equal to C2 equal to C3 is equal to 0 is one trivial solution, but we have also non-trivial solutions. So as a result, linearly dependent. So as Laura said that based on intuition, we understand it's R2, we have 3 vectors, they should be linearly dependent. They will be linearly dependent. And then we come to the concept of basis, which you are kind of familiar in physics or undergraduate algebra with that one. Basis of vector space. In
Excuse me.
yes,
Sorry. Please, could you just go over that explanation right there?
this one. This.
Yes.
We said that we have a feeling that these are linearly dependent. Why? I mean, a bit later when we are talking about the basis, we say that if they are in R2, we can have maximum 2 vectors which is linearly independent. Here we have 3 vectors, so we understand, we have this feeling that they are linearly dependent. So there are 2 forms of doing it. One is that I mathematically prove it, which I can do it now, or I come with a counterexample. And this is a counterexample. One example is enough to find C1, C2, and C3 are not all 0 at the time, and the result of the additions is 0. This is one example. Actually, as I said, we can see that it exists in a form, in a parametric form. So we have lots of values of C1 and C3 which are not 0, but the additions of all make 0. Or mathematically, you can write it in this form. Minus 2 C1 minus 1 C1 minus 2 1 plus C2 minus 1 minus 3 plus C3 4 and minus 2 is equal to 0, 0, which results into this. Minus 2 C1 minus C2 plus 4 C3 is equal to 0. Then we will have C1 minus 3 C2 minus 2 C3 is equal to 0, right? Now, in order to solve this one, we can, whatever we want to do. Let's say I multiply this one by minus 3, and I add these two. Then what happens is, and if I add it, this is 6, 7 C1, this is 0, plus, is this minus 12, minus 14, C3 is equal to 0. So I get that C1 is minus 2 C3, right? So, what about C2? I said that, okay, C2 is the parameter S. If C3 is T, C1 is minus 2T. So, one trivial solution is that S and T are 0, but we easily get that if we keep S 0, we can have T any other number. So this shows that they are linearly dependent on each other. Because if they wanted to be linearly independent, you know what would happen? We would come with a solid conclusion that you solve the system and you come with the C1 is 0, C2 is 0, C3 is 0. We do an example after I define the basis. So either you can see the example and you just put it, or you just simply solve it. Remember, if you come with a parametric solution, it means that 0 of course is the solution, but you have a non-zero solution also. So we want to define basis. We want to define a basis. In vector space V, the set of vectors V1 till Vn are called basis of our vector space V if we have two conditions. One, V1 till Vn are spanning V. In other words, V1 till Vn they belongs to V, and any vector in V can be written as linearly a combination of all the V's. Second thing is that V1 till Vn are linearly independent. In other words, we easily can see that the previous example, U1, U2, U3 are spanning R2, no problem. But the problem is that they are linearly dependent, so they cannot be a basis. Previous example, we could see that U, V, and W were spanning, and actually they were also linearly independent if you wanted to solve. So this has actually two properties inside itself. One is that V1 till Vn belongs to Rn, and then for any U belonging to V, we get that U is C1 U1, C1 V1, Cn Vn. This was the definition of a span, and then if they are also linearly independent, we get that they are bases. Bases are very important for us in general. Why bases are important? Bases because in a set of, for me, representing huge set of vectors, in a set of representing whole my vector space, I can represent it with these bases, and I can say that anything that I have here has been linearly combined. So if somehow I just keep the coefficients and the bases, it means that I can actually compress the huge amount of data that I have. Or if you are doing some learning and we are creating some dictionary, instead of keeping huge amount of data, I can basically keep the whole basis of this n-dimensional data that we have. Number of basis vector is called the dimension of the vector space. So a vector space is called n-dimensional if we have n bases. N bases. We knew that this belonged, the previous example belonged to R2, and because it was R2, the dimension was 2, we were expecting to have the bases to be 2. That's why that when we have 3, we had the feeling that they have to be linearly dependent. So let's do a few examples. Are the basis vectors unique?
No.
No. Very good. Example. vector space R3. R3 is spanned by famous I, J, and K vectors, right? And the dimension of R3 is 3.
So the notation that something is spanning a particular vector space is the vector space equals spanning.
Yeah, I mean, this
Okay.
means that these vectors are spanning R3. Remember, bases are subset of S-span. For vector space R 2 by 2. Do you know what are the elements of our span? I mean, the easiest form is something like this: 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. And the dimension. What is the dimension of R2 by 2?
Cool.
4, because we have 4 elements. And we know we can see that all of them are linearly independent. Vector space of P2 in R